All right, folks. So we're gonna jump back into the second part of class, and we're gonna be taking a look at 12.4, which is where we talk about hyperbolas. Okay, so it is the last conic section that we will be covering, and then tomorrow and on Monday we'll get a chance to look at a topic called rotation of axes. Okay. So I'm going to go ahead and share my screen so we can take a look at those notes. All right. So here we go. I hope your brains are feeling up to this. All right. So we've got this last shape, which is called a hyperbola. Okay. It is the situation when you have a slice that goes through not just one, but two of your cones. All right, so remember our cones are kind of stacked with the pointy ends together and then the circular bases on the outside. And when we take a slice that goes all the way through both of them, we end up with two hyperbolas, or well, two branches that create a hyperbola. And so when we have our hyperbola, we have some similar features to the hyperbola. We have a center, okay? So the center is where we graph first, and we graph everything else around that. We can find that from the equation once we complete the square. The next feature that a hyperbola has, it has one vertex over here, and it has a second vertex over here. So it has a pair of vertices. The third feature that this hyperbola has is that it has one focus that is kind of how like the focus was for the parabola, like on the inside part of the curve. And then because there's two branches, there is a second focus for the second branch, okay? Now you can have hyperbolas that open side to side, like this top case, or you can have parabolas that, we can have hyperbolas that open up and down, okay? So kind of like the parabola, you can open side to side or up and down. Now, the top case, where it opens side to side, you're gonna know that it opens side to side when in your equation, you're gonna have the x squared comes first in the equation, okay? Now, after you complete the square, if your y squared comes first, that means you're gonna have a situation where your hyperbola branches open up and down instead, okay? Now, in addition to the center, the vertices, and the foci, there are also a pair of asymptotes. I just want to highlight those to make sure that we see them. We have one asymptote. We have one asymptote here, and we have a second asymptote here. And when we draw our hyperbola, it's often helpful to draw those as guiding lines for the hyperbola. And then even if it opens up and down, you still have your two asymptotes, okay? So that top picture is probably good for those of us who are pretty visual, and maybe this bottom table is helpful for those of us who like to deal more with equations, okay? But you'll notice one big difference between the hyperbola and the ellipse equation. And this small difference makes all of the difference in the world. This right there is not a plus sign. If it is a plus sign, you have yourself an ellipse. If it's a minus sign, you have yourself a hyperbola. minus, and minus. Okay? All right, so let's go ahead and we're going to take a look at one last feature here that is very different, and that is the Pythagorean relation. So for the ellipse, it was a squared equals b squared plus c squared. Okay. For the hyperbola, it's going to be c squared equals a squared plus b squared. So the order that the letters are in are different. And if we were to write this out in words like we did the other one, C still stands for the distance from the focus to the center squared. Okay, so C squared is the distance to the focus squared. A squared is still the distance to the vertex squared plus the distance to the covertex squared. Okay. Now, the reason why it's C squared equals, or the focus squared equals, is because this time the focus has a greater distance from the center than the vertex does. So the focus is the longest distance along that major axis, okay? And in fact, we don't call it a major axis, we call it a semi-transverse axis, okay? But that is similar in idea to the major axis. Similarly, the semi-conjugate axis is similar in nature to the minor axis, okay? Now, there are equations here for you to fill in for your asymptotes, but we'll also talk about how we can write that out for ourselves using our point slope form, which this essentially is, and just from counting from our graph, okay? So let's get started with equation number 1, okay? So we've got 9x squared minus 4y squared. And immediately I'm like, oh, this is not going to be an ellipse. That minus sign right there is my first clue that I'm going to have a hyperbola. Now, I said earlier, like the letter that comes first tells us the direction that the branch is open in. But maybe to be more specific, the positive coefficient tells us which direction we're opening in. So the 9x squared, like that 9 is positive. So I know my branches are opening side to side, okay? So we need to have a case where we have something like this. And again, a lot of this pre-thinking is really important because we're sort of setting the stage for at the end, we've got all the information and now we just need to put it on a graph, okay? So let's take our equation. Let's do a completing the square at the very bottom like we did for the ellipses. And so when I write this equation down below, I'm going to keep the 9x squared where it is, but I'm going to bump the minus 36x next to it, okay? So kind of like an ellipse, I'm going to be grouping my like terms, so all the x's in the front, and then all the y's next, and then my numbers on the other side. So minus 4y squared minus 40y equals 388. Okay. So let's take a look at this completing the square here. The first pair, I can factor out a 9, and that's fine. What am I factoring out of the second pair?
-4.
I love it, a -4. That leaves us with a positive y squared on the inside and a positive 10y on the inside, okay? That minus sign makes things a little trickier. So just double check right here that when you distribute that minus sign back in, you're gonna get the right signs that you started with. All right, let's complete those squares. X squared minus 4x plus 4 minus 4y squared plus 10y plus 25 equals 388 plus 36, because 9 times 4, minus 100, because it's 4 times 25. Okay, so 9 and 4 make this 36. And similarly, negative 4 and 100 make this, and 25 make that negative 100 on the other side. And so let's write this as a perfect square. 9x minus 2 squared minus 4y plus 5 squared equals 388 plus 36 minus 100 gives me 324. All right, last step here. What do I need to do to get this in a form that is easy to graph?
Divide by 324.
Exactly. So when we divide and reduce, we'll end up with a denominator down here of 36. And in my head, I'm already thinking, okay, that's like 6 squared. Minus y plus 5 squared over 81. And I'm also thinking, okay, 9 squared equals 1. And so from here, I've got a center that is at positive 2, 5. Okay. So let's go ahead and rewrite this equation at the top so we can fill in the whole table. X minus 2 squared over 6 squared minus y plus 5 squared over 9 squared equals 1. I know my center is going to be at 2, negative 5. All right. I know my vertices. Okay. So here's another difference between ellipses and hyperbolas. The vertices are in the direction that your branches open. So since my hyperbola opens side to side, the vertices, I'm going to get them by taking the number under x and adding and subtracting that to the x value of the center. Okay. So my vertices are going to be 2 plus or minus 6, negative 5, or negative 4, negative 5, and 8, negative 5. It's not the bigger number for hyperbolas. It's in the direction that it opens. So like these vertices are going to be here and here. Okay. The co-vertices is whatever direction it doesn't open in. And so I'm going to use this 9 to add and subtract that to my y value of my center. So 2, negative 5 plus or minus 9 gives me 2, negative 14 and 2, 4. Okay. So before we find our foci and our asymptotes, let's actually plot our center, our vertices, our co-vertices, so we can start to get an idea of what this looks like. So I've got my center at 2, -5, so 2, -5. I've got my vertices at -4, -5, and 8, -5. And I've got my co-vertices at 2, 4, and 2, -14. And instead of connecting those and making it into an ellipse, right? We know it's not an ellipse, we know it's a hyperbola. We're going to go ahead and use those to draw a box. And so the box is going to look something like this. Okay. If you've been wondering where those diagonals come from, like where did those asymptotes come from? The asymptotes are the diagonals of this rectangle. So one asymptote is going to go like this, from one corner through the center, through the other corner. And then the second asymptote is going to go in the other diagonal, from that corner through the center, through the other corner. Okay. Now, if we wanted to sketch in our hyperbola, we would have something that kind of looks like this. That's like one branch of it. And then on the other side, we have another branch like this. The last two pieces that we need to have the coordinates for the foci, and we need to write the equations of the asymptote. So to find our foci, we're going to go ahead and use that Pythagorean relation, which is c squared equals a squared plus b squared. Okay, so it's a different Pythagorean relation than the ellipse. And I know that my c squared is going to equal 36 plus 81. It's just the two denominators, that's it, 36 plus 81. And so that's going to give me c of the square root of 117. And because those are along the semi-transverse axis, I want to go ahead and add and subtract this to the x value of my center. So 2 plus or minus root 117, comma, -5. All right, and root 117 is about 10.8. So that gives me 2 minus 10.8, which is -8.8, comma, -5. And 2 plus 10.8 is going to give me 12.8, comma, -5. So let's see, 12.8 would be somewhere around here, and -8.8 is somewhere around here. And so that's where our foci are for this hyperbola. Okay. The last thing that we need here is that we need to find the equations of the asymptote. All right. What point do both asymptotes go through?
The center.
Perfect. Okay. So that's why there's the h comma k in the equations for the asymptote. But we can think about this as go back to that point slope form, where we have our y minus y1 equals mx minus x1. And we just need to fill in the center for our x1 and y1. And then our slope is going to be the rise over run of our yellow asymptotes. And we can count that from our graph, okay? We can also count that from some of the numbers that we've seen in the problem. So we get y minus -5 equals x minus 2, and we'll leave a space for the slope. But the slope of this yellow line, it has a rise of 9 and a run of 6. If I literally count from the center to this corner, I went up 9 and over 6. That's how I got there. So the slope here is going to be 9 over 6. But it turns out if I choose the second asymptote, that's going to be -9 over 6. So I can just do a plus or minus in here, and I've got both equations for my asymptotes in one. All right? Now I think this one is pretty easy to say, like y plus 5 equals plus or minus 3/2 x minus 2, okay? But you really don't need to do much more than that to get the equations of your asymptotes.
Professor,
Yes.
can you explain again how did you find the slope?
I counted on the grid, like to go from this point to this point, how many boxes did you go over and how many boxes did you go up? It's just using rise over run.
Okay, thank you.
Okay. Yeah, I think it's important to remember that even though we've been through Calc 1, some of these basics like rise over run is still how we can find slope if it's a linear function, okay?
I have a question.
Yes, what's up?
So because you want to, would we be penalized if we put down y plus 5, or do you want it to be in that true point slope form?
What do you mean if you had y plus 5?
Because it's y minus the opposite of 5.
Right, so that's what we have here, yeah?
Could we put it either way?
Like, what are your two options?
Unsimplified?
Oh, yeah, you can. I think if it's like a distribution of signs, then that's maybe something that is worth doing. But if it's like in the earlier problems we saw with the ellipses and it was kind of like a distributing a gross radical, like that's probably not necessary. But if you have the first version, like I'm not going to take off point unless you have the wrong numbers in there. Does that answer your question?
Yes.
All right. Any other questions on this first example here? All right. Well, we got about 10 minutes left. I think we can crank out this second graph here and leave us in a good place for tomorrow, okay? So let's jump right in. I see that we've got a minus sign here. And so I'm thinking not an ellipse, but a hyperbola. And then I'm thinking which one comes first. The y squared comes first, but also which one is positive, y squared. So I'm going to end up in a situation where my branches open up and down, and that my vertices are going to be here and here. Okay, so I'm already making those decisions. It's a hyperbola. I know it opens up and down, and I know where my vertices are. So let's complete our square. We've got 9y squared minus 36y minus x squared plus 12x. And I'm going to take that 36 and I'm going to add it to the other side. All right, let's factor. 9y squared minus 4y minus parentheses x squared minus 12x. All right, so we need that minus 12x there, equals 36. And now let's complete our squares. 9y squared minus 4y plus 4 minus x squared minus 12x plus 36 equals 36 plus 36 minus 36. This becomes 9y minus 2 squared minus x minus 6 squared equals 36. And so my last step is to divide both sides by 36. So I get y minus 2 squared over 4 minus x minus 6 squared over 36 equals 1. Now, when I rewrite this at the top, I'm going to change my denominator from 4 to 2 squared and my 36 to 6 squared. So I can start to think about which numbers are going to be useful when I need to graph. Okay? So y minus 2 squared over 2 squared minus x minus 6 squared over 6 squared equals 1. Coordinates of the center.
Six and 2.
6, 2. I'm so glad you said that. I actually would have been glad if you said 2, 6 as well, because that would have been the #1 wrong answer. Okay, so we don't just read from left to right. We got to think about what's an x, what's a y. And so our center is going to be at 6, 2. And I'm going to go ahead and throw that on my graph. So I have that 6, 2. All right. So to find my vertices, I'm going to take the number under y, and I'm going to add that to the y value of the center. So that's going to give me 6, 2 plus or minus 2, or 6, 0, and 6, 4. And I'm going to go ahead and put those on the graph as well. 6, 4, 6, 0. All right, my co-vertices then are the other ones that help me draw the box so that I can draw my asymptotes. So I'm going to take the number under x, which is 6, and I'm going to add and subtract that to the x value of the center. So I get 0, 2 and 12, 2. Oh, shoot. So 0, 2 and 12, 2 is out there somewhere. Now, if we were to find our foci right now, we would want to remember that it's c squared equals the 2 denominators added together. So that's going to give me c squared equals 4 plus 36, or c equals the square root of 40. Okay? And I am going to add and subtract this number from the y value of my center. so that's going to give us 6 comma 8.3, and 2 minus root 40 gives us 6 comma negative 4.3. And so I could draw those in. 6 and negative 4.3 would be down here, and 6 and 8.3 would be somewhere up here. And now we're going to draw the box. And that box allows us to draw in our asymptotes that go along the diagonal. Close enough. And then from there, we just sketch in our hyperbola branches. So one up here, and one down here. Okay. All right, last piece, we're going to write the equations for our asymptotes. So I know that it's y minus my center y value, which is 2, equals plus or minus. I'm going to need a rise over run, x minus 6. So let's zoom in and see if we can count that rise over run. So let's go from here to here. I'm going to go up 2 units and over 6 units. So my rise is 2 and my run is 6. I could reduce that to 1/3 if I want, but I'm going to leave it as 2/6 right now, just so when you go back and think about where it came from, we didn't count 1/3, we counted 2/6, okay? And then if we counted the other way, like from here to the center, we would go down 2 and over 6, so it would be negative 2/6. And you can write this as y minus 2 equals plus or minus 1/3 if you'd like, but there's nothing wrong with leaving it in the unreduced form, okay? So I know we kind of rushed through that second example, but I wanted to get through as much as we can today. If you have questions on the graphing of the hyperbolas, we can certainly address them at the beginning of class tomorrow. Tomorrow, when we start off, we're going to have 3 more examples where we work on writing the equation of the hyperbola from given pieces of information. And that will round out our experience for conic sections in terms of graphing and such. We're not going to do any applications for hyperbolas to calculus. Those will be focused more on the parabola as well as the ellipse, okay? So I'm going to stop the video here, and